In this video, we're going to cover section 3.4 on optimization, finding absolute maximum and minimum values. So it's a kind of a continuation of what we've done so far in chapter 3, only so far we've just talked about relative maxes and mins. So this is how to find, when possible, absolute maxes and mins. So our objectives are to learning how to find the absolute maxes and mins using principle 1 versus principle 2. So basically there's two different options here. All right, so the definition, suppose that f is a function with domain I. F of c is an absolute minimum if f of c is less than or equal to f of x for all x's in I. So the only difference really between a relative or relative extreme values that we found in the first few sections and an absolute extreme value is that relative could mean just the lowest or highest point within a subset of the domain, and an absolute max or min is overall the entire domain, what the max and the min are. So there's no of some smaller set here. That's the only difference in this definition. So the lowest value of the entire function over the domain, and an absolute max is the largest value, or the case where f of c is greater than or equal to all other f of x within your interval. All right, so the next theorem we have is called the extreme value theorem. It says that a continuous function, f, defined over a closed interval, that is important, must have an absolute max value and an absolute min value on that interval. So when we're defined on a closed interval, where we're defined at the two endpoints being numbers and at all numbers in between, there's definitely an absolute max somewhere and an absolute min somewhere. All right, so principle number 1 says, suppose that f is continuous, defined over the closed interval AB, which means it's definitely going to have a max and a min. To find the absolute max and min values over that interval, we start by finding the first derivative. So find f prime of x. Second, then determine the critical values within the interval. That means finding all c in the interval for which the function is either equal to 0 or doesn't exist. Those are the critical values that we've talked about in the previous sections of this chapter. So the possible locations for relative maxes and mins are also possible locations for absolute maxes and mins. List the values from step B, meaning all your critical points, C1, C2, up to however many there are, and the endpoints, the A and the B. So an absolute max or min could occur on the interior, like the relative maxes and mins, or it could occur at the endpoints of the closed interval A and B. So those are your candidates for where they might happen. And then to decide which is the max and the min, you're going to evaluate the function for each value listed. So for the f of A, f of every critical value you found, and then find f of B. So plug all of those critical values and the endpoints back into the original function. And the largest of those values obtained would be your absolute max over that interval, and the smallest output value from plugging them into f would be your absolute min. Okay, so we're going to find the derivative, use it to find critical values, plug in the critical values and the endpoints back into the function, and look for the largest value and the lowest value. All right, so first example. Find the absolute maximum and minimum values of this function over the interval -2 to 3/2. All right, so the first step, find f prime. So our first derivative of this function would be 3x squared minus 3. That exists for all real numbers, so we will just set it equal to 0 to locate our critical values. So if I add 3 to both sides, divide both sides by 3, and then square root both sides. So my critical values are plus and minus 1. So I'm going to list my critical values, -1 and +1, along with the endpoints of the interval, -2 and 3/2. And then I'm going to evaluate my function f at all of these values. So plug them all into f separately. So f of -2, we get 0. f of negative 1, we get 4. F of positive 1, we would get 0. And f of 3 halves, we would get 7/8. Notice these are getting, this last step you're plugging into f, not f prime. All right, so it looks like my largest value here is 4. So that would be my absolute max. That occurs when x is negative 1. And my lowest value is 0, and it occurs at 2 different x values. So 0 occurs at both negative 2 and positive 1. So the absolute max of the function on this interval is 4, which occurs at x equals negative 1. And the absolute minimum on that interval was 0, which occurs at both negative 2 and positive 1. So the actual max or min value is the output that you get from plugging into the function, and it occurs at whatever x you had plugged in to get that. All right, we're going to do another example. Find the absolute max and min of the functions given in example 1 over a different interval, this time over the interval 0 to 3. All right, so from example 1, this was our function. So that was my derivative. And we set it equal to 0, just like before. We get plus and minus 1. So that those steps would not change. All right, next we're going to take the endpoints of the interval, which were 0 and 3, along with our critical values. Now notice negative 1, one of these critical values lands outside of the interval, so I really didn't even need to list this one because I'm only looking for what happens in between the 0 and the 3, but they went ahead and listed it, but you could have omitted that. They went ahead and found it and got 4. F of 0, 2, f of 1, 0, and f of 3, 20. Now notice this one didn't matter because it's at that x value is outside of my interval, so if that had been a max or a min, it wouldn't have been counted. So they really shouldn't have even done this because it's not relevant, because it's not in between 0 and 3. This x value is not. So really the only ones to consider are the 2, the 0, and the 20. So the min is the 0, it occurs at 1, and the max is 20 that occurs at 3. So the max being 20 at x equal 3, and the min being 0 at 1. All right, principle 2 says, suppose that f is a function such that f prime exists for every x in the interval, and that there is exactly one critical value for which f prime is 0. So if you only have one critical value to consider, then that critical value is an absolute max if the second derivative is less than 0, meaning if the graph is concave down at that point, and it is an absolute min if the second derivative is positive or greater than 0, meaning concave up. So if you only have one to consider, you can use your second derivative test. This does not work if you have more than one. As we saw in previous sections, you could have it concave up or down, and it would matter as far as comparing the outputs. So this only works if there is exactly one critical value in your interval. So find the absolute maximum and minimum of this function over the interval negative 2 to 1/2. All right, so we need to find our first derivative. So the first derivative, the 2 would just stay in the front. This derivative would be e to the 3x times 3. That's the derivative of the exponent, so that times 3 and this 2 is where the 6 comes from. Note that this function is greater than 0 for all x, okay, meaning that there are no critical values here. Setting this to 0 gives me no solution, but no matter what x happens to be, I get a positive number. So there are no critical values, and the absolute extreme must occur at the endpoint. So if I don't have any critical values, in other words, there's no solution to setting it equal to 0, then I don't have any numbers to list as critical values, but I still have to check my endpoints. So we just have to plug in the endpoints of the interval, negative 2 and 1/2, back into the original function, and then compare. So when I plug negative 2 in, we get about 0.005, and when I plug in 0.5, we get about 8.963, which would mean this is the max, 8.963 occurring when x is 1/2, and 0.005 is the min, and that occurs at negative 2. So the maximum is the 2e to the 1.5 occurring at a half, and the minimum is 2e to the negative 6th occurring at negative 2. So even if there's no critical points here, don't forget you always have to also consider the endpoint values. All right, so the strategy here is to find absolute max and min of a continuous function over an interval. Find the derivative first derivative. Find the critical values. If the interval is closed and there is more than one critical value, you have to use principle 1, where you list all the critical values and the endpoints and plug them all in and check. If the interval is closed and there's exactly one critical value, then you could use either. You could still do it the way we did the first example, or you could use principle 2. If it's easy to find your second derivative, then this principle number 2 will be faster, where you just check the concavity at that point. All right, so find the absolute max and min of this function over the interval 0 to infinity. Now notice here, this time my interval is not closed. So that means I'm not necessarily guaranteed to have one. All right, so f prime, derivative of 5x is 5. To do this derivative, you would have to bring this up as an x to the negative 1. Then doing your power rule would bring down the negative 1. That's where you get negative 35. This would then become x to the negative 2, and then moving it to the bottom, making it a positive 2. That's where that comes from. Since f prime exists for all values in the interval 0 to infinity, this is the interval we're concerned about. This does not exist when x is 0, but notice 0 is not included. The only critical values we'll find on that interval will be the ones we get by setting it equal to 0. So if we set that equal to 0, we can add the 35 over x squared, multiply both sides by x squared, divide both sides by 5, and then take the square root of both sides. Notice taking the square root would technically give you plus or minus 7, but the interval they gave us was 0 to infinity, so that negative square root of 7 wouldn't have even mattered. Remember how they did that problem earlier where they used a number not in the interval, and I said they really shouldn't have? Here they've actually done it the right way and not even listed a number not in my interval given. All right, so the interval 0 to infinity is not closed, and the only critical value is square root of 7. So we can use maximum, that second principle, using our second derivative, because we only have one derivative to check. So f double prime, the second derivative, we get 70 over x cubed. So we're going to plug our critical value into that second derivative. So my critical value being square root of 7, there's only one. So that's going to give me a positive number. So since that's positive, think of second derivative being positive means concave up. That's the bowl, which would mean you'd have to have an absolute min at your critical value. So the f of the square root of 7, plugging that back into f, gives me 5 square root of 7, and they rationalized the 5 over square root of 7 and simplified it and gotten 10 square root of 7. So that is the minimum value is 10 square root of 7, and it occurs when x is the square root of 7. All right, and it has no max. Remember, we were not guaranteed a max or a min if the interval was not closed. We don't check endpoints if the interval is not closed. So it has no max value. All right, find absolute max and min of this function on the same interval. Okay, so this is similar. If you want to try this one on your own, you can pause the video, work through the steps that we did on the previous example, and then press play to check your answer. All right, our first step is to find g prime. So this time to find g prime, notice it's a quotient, so we're going to use the quotient rule. So the derivative of the top is the 4x times the bottom minus the top is all this times the derivative of the bottom would just be times 1, and then divided everything by the bottom squared. So that's our quotient rule formula. Distributing the negative sign through the numerator and cleaning up the first term to be 4x squared, combining like terms, then setting that to 0 here. This is what they got. Instead of factoring anything else here, they just, since you have a single denominator, they just split it up as 2x squared over x squared plus 18 over x squared. It's an easy way to simplify a little bit. So these canceled and leave the first term being 2 minus 18 over x squared. We're going to set, so this is just simplifying right here. This is what we had. They're just splitting it up and reducing it, then setting it to 0. So adding the 18 over x squared to both sides, multiplying both sides by x squared, dividing by 2, and then square rooting. So we get plus or minus 3. So remember, the interval given was 0 to infinity, so negative 3 is not in the interval, so we don't even need to use that one, so the only critical value is at 3. So again, one critical value in our interval, we can use that second principle. So the second derivative is 36 over x cubed. Plug in your critical value. That's a positive number. So that's, again, positive second derivative means concave up, meaning we have a min. So an absolute min occurs when x is 3, and the min value is 12, because if you plug 3 back into the original function, you would get 12. And again, since it's on an open interval, we don't check endpoints, and so there's no max. All right, so that is it for this section. So our summary here, an absolute minimum of a function is a value that is smaller than the function value at that point is less than or equal to all other function values on the domain. An absolute max of a function is a value f of c that is greater than or equal to all other function values. So over the entire domain, the absolute largest and smallest are your absolute maxes and mins. If the domain of f is a closed interval and f is continuous on the domain, we use that extreme value theorem, and we know we're going to end up with both a max and a min. Endpoints of a closed interval may be absolute extrema, but not relative, so we check them for the absolute max and mins, but remember we didn't even consider them for the relative maxes and mins because they don't really matter. And if there's exactly one critical value such that the derivative is 0, then you can use principle 2, meaning the second derivative, to see if you have a max or a min. All right, so that is the end of section 3.4.